Hi class, we are starting section 12. Chapter 12 talks about PDEs, partial differential equations. So let's go ahead and get started. So the general form of a linear second order PDE is as such. Okay, so this is in the partial form. Okay, and so I will also provide you with the subscript form. Okay, so we have the Leibniz notation, and I actually don't know what this notation would be called. So the second partial of u with respect to x, or uxx. So these a, b, c, d, e, f are functions. Okay, they could be constants, they could be real valued functions with variables of x and y, so they can be multivariable functions. And then g is our forcing function, right? Also a multivariable function. When a, b, c, d, e, and f are constants, solving these are not super difficult. When they're functions, it's extremely more difficult. Okay. So here, if this g function is 0, then just like before, our PDE is homogeneous. If it is not 0, then our PDE is non-homogeneous. Okay, so again, a lot of the notation that we have for what we've been doing so far still stands, right? The linear combinations, the linear independence, the superposition principles, all of those still apply here, right? Solutions to our PDEs are a multivariable function which we call u. Okay, u is has independent variables of x and y, which is why we can differentiate u with respect to x or y in several different ways, either as a single partial, as a mixed partial, or as a partial in one direction as a second derivative, right? So this is in the direction of y 2 times second derivative. Generally, we are interested in particular solutions, not in the homogeneous solutions. Okay, so generally we want the particular solutions to the non-homogeneous equation. That's generally what's more interesting to us. If I continue this video series throughout chapter 12, then we'll talk about that for the classical PDEs that we come across. But for right now, we're going to kind of just focus on a single method of solution. Okay, that method is separation of variables. Okay, so typically what happens is I would like to take this equation and I would like to separate it into functions that are dependent in x and functions that are dependent in y only. Okay, so I'd like to take my u function and break it into a product of some function only in x and some function only in y. For notation simplicity here, the function that is dependent on x is big X, and the function that's dependent on y is big Y, right? So I like to separate this into 2 functions, one completely in x and one completely in y. Now, if I take this function and I take its derivative in terms of x, if you remember your calculus 3, that means that this is held constant and this turns into a derivative. So I basically have a constant times the first derivative of my x function, right? The derivative with respect to y, this is held constant and this is my derivative, right? Second derivative is the same thing. This is a constant and this is the derivative is taken twice. And the same thing for the second partial of y, okay? Or in the direction of y, I should say. So generally what happens is that once I'm able to kind of make these substitutions back into my equation here, I should be able to separate my problem into 2 ODEs. Okay, so if you don't remember what ODEs, it's everything else that we've been doing. Okay, everything up to this point has been ordinary differential equations because there have been no partial derivatives present. Okay, so that's kind of a big deal because we're going to take our PDE and turn it into 2 separate ODEs, which we then know how to solve, right? So I kind of skipped some sections at this point in time to come to this chapter. But in the previous chapters, we talk about how to put those 2 separate solutions to the 2 ODEs that we're going to get and how to put them together as a solution, right? So if I update this video series, in the sections where we talk about the Fourier series, that's where we kind of come together to talk about the solutions here, right? So if you're interested in that, you can look at my my section in my linear algebra playlist. I have a section on inner product spaces, and that's highly applicable to what we would be doing in this case. Okay, so if A, B, C, D, E, and F are scalars, okay, real values, constants, that's kind of the best case scenario, right? Then what's going to happen is that our equation here can be reduced to this form when I substitute in my functions for u. So when we make our substitutions, this is what it's going to look like, right? So we got the u double x, so that's the x double prime, or second derivative of x, and the y was constant. Here we got the mixed partials, or the mixed derivatives, I should say. Here x is as it was, y is the second derivative, and so forth and so forth. Okay, so we plugged everything in. Remember, u is a function of x and y. I know everything is capital, so it can get a little confusing, but please remember that A, B, C, D, E, and F are all coefficients, right? They are constants. They are not functions. Okay, they're not functions of x, not functions of y, or any combinations of those. X is a function of x only. Y is a function of y only. Okay, so as we go through, that'll be very important. So our goal here is to separate the x's and the y's. Now, obviously, that's going to be very difficult because there's a mixture of x and y's everywhere. We can't just pull out a factor of x because this function has x, this function has x, this function has x, but all the others have x primes or double primes. Same thing with the y's. Here's a y, here's a y, and here's a y, but then we have y primes and double primes. So we can't just say, oh, I'm going to factor all the x's out and factor all the y's out. So what we're going to do is, if you remember, a lot of times we like to make our differential equations monic. We would like this to be just x double prime. So what we're going to do is we're going to divide by a times y across everything. Okay. However, we're going to add to that x. So we're going to divide by axy, because what that will do is, one, it will turn this into a function of just x prime, or a function of just x, because this will turn into x double prime over x. The a and the y will cancel. Here, this will still be a mix because it'll have x and y in the denominator. Here, the x's will cancel and it'll turn into a function of just y's. Here, the y's will cancel and it'll be a function of just x's. Here, those two x's will cancel and it'll be a function of just y's. Here, the x and y will cancel and it'll be a function of just f. So, dividing by a, because it's in the first term, and the standard functions x and y with no derivatives, allows us to get a lot of this stuff into functions that are only x, okay, or only y. And the only one that's left that has x's and y's is 1. There's only one left. So dividing by axy helps us to start that division, okay? So remember, f and a, these are constants. So this is just a constant term. This is some constant coefficient. This is some constant coefficient, and this is some constant coefficient. Okay. So since this is the only one that's mixed, okay, I would like to get this to not be in terms of x and y, right? So what I'm going to do, okay, again, a can't be 0 because it's on the denominator, okay? So what I'm going to do is I'm going to differentiate with respect to x, okay? So this whole function here, I'm not going to actually do the product rule. I'm just going to say, hey, this rational function here should be to the derivative, okay? This will be to the derivative. This will be to a derivative. These ones will go away, okay? Because these are considered constants, okay, in terms of x. This is not a function in x. This is not a function in x. This is not a function in x. It's a constant. So this one, and this one will all disappear. Okay, so that's helped me to reduce my equation down quite a bit. Okay, and now this is the only one that's mixed. Okay, so if everything else is functions of x except for this one, what I'm going to do is I'm going to divide by its coefficient. Okay, because then this will no longer have something with x attached, right? So the b over a and the x prime over x prime, I'll divide by. So what happens is when I put this on the denominator of everything, this will be a function of x only, this will be a function in x only, and this will become a function in y only. Once I can do that, I can separate it to functions of x's only and functions of y's only. Okay, so I'm going to divide by its coefficient term with respect to the y's here, and that will allow me now to have function in x. This actually, the x's all cancel because this x prime over x prime being divided on both sides goes away. So this is a constant, this is a function in x only, and this is a function in y only. So now, in order to finish separating them, I would like to have all the x stuff on one side, all the y stuff on the other side. So I'm going to take this y prime over y, and I'll move it to the right hand side of the equation. Okay. So we move it to the other side, it becomes negative. And so let's think about what we have here so far. Okay, I have a function in y only and a function in x only, and they're being equal. How can a function in y only be equal to a function that's only in x? They're completely different variables, right? The only way for that to happen is if this is equal to a constant and this is equal to a constant. So we set that constant as lambda. Okay, lambda is a constant. That's the only way for two functions in different variables to be equal to each other. Okay, so what we can do now is I can now separate this into into two separate equations. One as a function of y only, negative y prime over y is lambda, and the other equation as this crazy thing equals lambda. Okay, the first one is easy to work with. We've talked about it a lot. We had a whole section on first order differential equations. This creates a first order differential equation for me. Okay, the second one is the one that we're going to work on. Okay, so this gives me negative y prime equals lambda y, or I can move it over to all the y stuff being on one side, and we have y prime plus lambda y equals 0 as one of our ODEs. That's a very, very easy one to try to solve. We have several methods for solving these kinds of things. We really already know what this looks like, right? The solution basically looks like e to negative lambda, right? So there we go. Okay, right? We've seen these before. So that's nice. So now we need to focus on the second one. Okay, we have our first one. We know what the solutions pretty much look like for this. So the other equation that we want to worry about now is this left-hand side minus lambda equals 0. Okay, so again, moving everything over to one side. So again, notice that d over b is not a function. This is a constant. So I have some constant minus a constant. So I have a function in terms of x plus some constant equals 0. Okay, so we like to move this around so it's something easier for us to work with. Okay, so we are obviously going to get rid of this denominator here by multiplying it out. So I now have my first term back to how it was, plus this constant times what I had in the denominator. So again, notice that this whole thing, d over b minus lambda times b over a, all of that is a constant. Okay, so again, we're working with things in general terms, so they can get a little bit messy, right? So what I'm going to do is I'm going to integrate this. Okay, so I have one term that's to a derivative plus another term to a derivative. So taking the integral just helps me to undo that derivative that I took way back over here. Okay, so remember, I really did this just to help me get rid of some stuff so that I can separate my equations. So me taking the integral kind of helps me bring it back to things that are easy to work with, especially since each term has a derivative present. Taking that integral just allows me to get to the functions that I want to actually get to without having to do the product rule and all this kind of stuff, right? Sorry, I meant quotient rule, right? Because these are quotient functions, these are rational functions, so not the product rule, quotient rule. So taking the integral here, we'll just get rid of these prime terms, not the terms, but the prime notations, and then I'll have some constant of integration being added, right? Which we will call beta. This equals 0, so taking the integral of 0 will still be 0, right? So I'm still working with a function, taking its integral, adding that constant of integration, okay? So what I'm going to do is I'm going to take this y prime over y equals negative lambda, right, that I got from up here, okay? And what I'm going to do is I'm going to substitute that all the way back into my original equation here, okay? I'm going to bring that all the way back into here. Since that was the original equation that I was working with, and I came up with some sort of equivalency for one of those terms, right? Y prime over y. So you see that shows up kind of in two places. This is y prime, double prime over y, so we'll talk about how to work with that in a second, okay? So substituting my left-hand side, my right-hand side, I'm sorry, back into my original equation, we'll get rid of, again, these y prime y terms, and this y double prime over y term actually, and it will look like this, okay? So y double prime over y is actually lambda squared, okay? This e over a, negative lambda, right? And then this y prime over y here gives me the ba over x prime x times negative lambda. So what I'm doing is I'm taking my substitution and I'm bringing it all the way back. Now, you might be saying, well, what about this thing? This is going to come into play later. We're going to work with our original equation a little bit, and we'll show some equivalencies from this thing to this thing. That's going to allow us to find out what this beta value is. Okay. So the next question you might have is, how the hell is y double prime over y lambda squared? Okay. So we know that y prime is negative y lambda. Okay. So if I take the second derivative of this, right, I'm going to get negative lambda times y prime, right? Because lambda is a constant, y is a function of y. I know what y prime is, it's negative lambda y, right? So I'm going to substitute that into here, right? And so that's going to give me, here we go, y double prime is, well, look what we get here. This is lambda squared, okay? Lambda squared times y. So y double prime divided by y is lambda squared. Y double prime over y is lambda squared. Okay, there we go. So that's how we figured out what that constant value is going to be. So now, again, I have a function in only x's from my original equation, right? So from my original equation, I found I separated it into y's only. I came back and found something for x's only. Okay, and I actually did that again here, right? This is an x's only as well. So we're going to work with this thing to figure out some more information about this, basically. So I'm going to take what I have, okay, and I'm going to multiply everything times a times x, right? I would like to not have any denominators, if possible, right? Just like we did for this y prime plus lambda y equals 0, we got rid of the rational function notation. So I would like to get rid of that. So I'm going to multiply everything times a times x so that I don't have any more fractions. My function in x is no longer in the denominator, right? So we multiply times x everywhere, okay, not by a, sorry. So I got rid of the rational function portion, c over a, d over a, e over a, f over a, b over a. Those are just constants, right? So I got rid of x in the denominator, and now this looks more like a differential equation, right? I have some primes here, okay, and I got functions in x here. Okay, so what I'm going to do is, you can see they're already grouped together, right? And it's going in descending order, x double prime, my two prime functions, and my just x functions. So let's pull out those terms and group what we have together, right? So I pulled out x double prime of everything. All of these have a on the bottom, so I put 1 over a in front here, 1 over a in front here. I'm left with my lambdas and my C, E's, and F's, and my B's and D's. Here, since D is negative, I'm sorry, D is positive, but B is negative, I switched their order so that it flows a little bit better, right? So now if you notice, for this coefficient, we have it in polynomial form, right? And this is also in a polynomial form. So we have our constants here, right? So this first term here, okay, if I change it around a little bit and I pull out a factor of b, this is negative beta x. Okay, and here I just pulled out the c so that my lambda is now a monic polynomial, right? It divided it by its first term coefficient, right? Its leading coefficient. And so I pulled out that c over a factor. Okay, I did the same thing here. And so I'm going to scroll back in just a second, but notice again that if I had moved beta over to the right hand side earlier, here, okay, x double prime over x plus d over b minus lambda b over a x prime over x. So if I were to move beta over and multiply everything by x to get rid of this denominator, x double prime and x prime, then that means that this side on the right hand side would be negative beta times x, and I would have the exact same thing that I have over here. Let's go back this way. Okay, the same thing over here, x double prime d over b minus lambda b over a x prime. That is negative beta over x. So again, that's why we did this over here, so that we can make this relation later. Okay, let's go back here. Okay, so again, this is all one single constant. Okay, this is a single constant, but I know that this entire term is negative beta over x. So negative beta over x times some other constant times x equals 0. Okay, so if I make that substitution, this constant, this is also a constant. So some constant times x plus some constant times x is 0. Well, I can then relate those two constants, right? If I were to even just move this over, I would have this constant times x equals beta times x. So beta is the same as this term. Okay, so this whole thing here equals beta. So u of xy is a solution of my original general form if x being a function of x and big Y being a function of y satisfy this equation and also this equation, right? So my large X has to satisfy this and my large Y has to satisfy that. So again, this we can figure out what the solutions look like. This is a higher order second order differential equation. Again, this is just a constant and this is just a constant. So A, B, C, D, E, and F, all of those values would be given to me. Okay, a lot of times none of those functions are even, or none of those values are even possible, right? So it's very possible that I have something like 3u double x plus 2u double y equals 0. That means that B, D, E, this should be a capital F, are all 0. So a lot of these things would disappear, and then I can really just kind of go to my equation and say, okay, let me plug in A is 3 and C is 2, and then everything else being 0, now my differential equation that I need to solve, that second one, is very small, right? So using this is actually very, very helpful, right? So we did this in a general form, so you could use this for all of your separation of variables as long as this is the general form for your second order. Okay, again, this should be a capital F. Apologies on that. I don't feel like fixing it right now, but I will fix it because it's very minor. I will fix that, however, in the write-up in the Canvas document that I post for my class. Okay, so that's very helpful. Okay, again, this is a second order homogeneous equation. This is all a coefficient, right? And this is all a coefficient. You can solve this with all of those second order methods that we have, right? So that's very nice, and this is actually very easy to solve for as well. Okay, so let's talk about the other principles that are here in the PDEs. We'll go through this rather quickly. Okay, if U1, U2, and UK are all solutions to my homogeneous linear partial differential equation, then the linear combination of those is also a solution. Okay, again, the superposition principle. Here, C1, C2, up through CK, these are all constants. They're real scalar values. So my solution is really just the sum of each of those pieces until I reach K, right? So the reason why it goes up to infinity is, again, if we're talking about Fourier series solutions, okay, those go on forever. They're like series approximations, pretty much. Okay. So let's talk about classifications of RDEs, right? For second order linear general form. Again, this should be capital F. So I've been cutting and pasting with the small f here. I don't know how that came in. Everything else is a capital. Anyways, I digress. So if all of these are real scalar values, okay, then my DE can be classified as hyperbolic if, again, this should look very, very familiar, right, from algebra. If b squared minus 4a times c is positive, it's a hyperbolic PDE, okay? It's parabolic if that equivalent to the discriminant is equal to 0, and it's elliptic if that equivalent to the discriminant is negative, right? So I can classify it as hyperbolic, parabolic, or elliptic. And again, if you look at their phase planes, then it'll make a lot of sense. Again, that would have been chapter 10 in this textbook. So if I go back and go through that, we can this video would make a little bit more sense as far as these classifications. Okay, there you go. That's our first lesson for PDEs. I'll see you guys on the next video. Thank you.